Now let's discuss the general theorem. Here we have a general ordinary differential equation where the right-hand side is a continuously differentiable function of two variables. And we have the initial point, t0, y0. Well, basically the domain of the right-hand side can be some, well, let me plot. So imagine that the domain of the right-hand side is some open set in the plane ty. And then we have the initial point somewhere here. Well, but then in this big domain, which is an open set, there is a certain subset which is a rectangle. Okay? And this is a rectangle between alpha and beta in T and gamma and delta in Y. Well, what the theorem tells us is that with this initial condition, there exists a unique solution of the differential equation, but the domain of that unique solution, it can be smaller than the interval from alpha to beta. Okay, so it can be strictly smaller. So let me explain how it happens on some specific example. And so here is a differential equation. So let's think what the domain is. In this differential equation, there is a division, and the denominator may be 0. So if you equate the denominator to 0, so y times y plus t is 0. So it's either y is 0, which is this line, or y equals negative t, so which is this line. And so the domain of this differential equation is everything except for these two lines. Well, but then this is a huge domain, but within this domain, of course, you can think of some specific rectangle that is a subset of the domain where the initial point belongs to. So here is an example of such rectangle. But then, if you try to plot the solution of the initial value problem on the plane ty, right? So then it's going to be something like this. Well, then it's going you will be able to extend it. But then here it can only be extended up to the boundary of the domain, so up to the line y equals 0, and then it cannot be extended any further because there is nothing along the line y equals 0. Right? So notice that here this if this is t-axis, this is y-axis, so the domain of the solution is not the whole interval from 0.5 to 4, but there is nothing here. So between 0.5 and whatever this is, and this is about, I guess, probably 1.2 or something. So the solution is not defined when t is between 0.5 and 1.2. But it is definitely defined on a smaller interval. And so that's what the theorem is about. So it tells us that the initial value problem always has a unique solution, but the domain of that unique solution, it may be smaller than the domain of the right-hand side in T. And so let's go through a couple of examples of how we can apply this in practice. So here is a differential equation. Well, notice that first that there is division by y, and of course y cannot be 0. So which means that the right-hand side is defined when y is either bigger than 0 or smaller than 0. And since the initial point satisfies y bigger than 0, so we must have y bigger than 0. Well, but then we can solve this differential equation. So let me do it step by step, just to have one more example of separable differential equation. So when we separate the variables, we get the right-hand side becomes the left-hand side becomes y dy, and the right-hand side becomes 4 minus t dt. Then we integrate. Then the antiderivative of y is y squared over 2 equals 4t minus t squared over 2 plus constant. Then we can multiply by 2. So y squared equals 8t minus t squared. Well, if c is any number, then 2c well, is also any number, so I can just change the constant here. Okay, so y of 4 equals 4. Let's compute the constant from this condition. So y equals 4, so we get 16 equals 8 times 4. 8 times 4 is 32 minus 4 squared is 16 equals constant, and of course from here we see that the constant is 0. Sorry, plus constant, right? So c is 0. So in other words, y squared equals 8t minus t squared. So y should be equal to plus minus square root of 8t minus t squared. But it should be plus because y is positive. So therefore, that's the final answer. But note that for the square root to be defined, the expression inside the square root has to be non-negative. So which means 8t minus t squared should be non-negative. Well, but then solving this, we see that t should be between 0 and 8. But since y cannot be 0, and if t is 0, or if t is 8, then y will be 0, so which is not allowed, which is why inequalities become sharp inequalities. So that's the final answer. The t is between 0 and 8, so which means that here the domain of the solution is the interval from 0 to 8. So let's quickly go through one more example. Okay, so just as in the previous example, here there is division by 0, so which means that y is not allowed to be 0, but since the initial value of y is negative, it means that y has to be negative. But then when we separate variables and integrate, we are going to get this condition. And then we can solve for c by letting y be -2 and t be 0. And we can solve for c. So therefore, c has to be the cubic root of this 4 times t to the 4 plus 4t squared minus 8. But notice that it's not all, because remember that y has to be negative. So which means the cubic root, it preserves the sign of an expression, so which means that 4t to the 4 plus 4t square minus 8, it has to be negative. So you will have to solve this inequality. And when you solve this inequality, you will see that t has to be between -1 and 1 in order for it to be satisfied. So which means that the final answer is actually the interval from -1 to 1, and this is to ensure that y is negative. All right, one more little example. So if you consider this initial value problem, so note that here y is raised to the power 2/3. So then notice that, well, it has two different solutions. So let's just verify quickly that they're indeed solutions. So if y is 0, then 0 prime equals 3 times 0 to the power 2/3. Correct? Correct, yeah, so 0 equals 0. Okay, how about t cubed? So the left hand side is 3t squared. The right hand side is 3 times y to the power 2/3. So t cubed to the power 2/3. T cubed to the power 2/3, and here 3 cancels out, so 3t squared, correct. So it seems like we have a contradiction. So this initial value problem has two different solutions. Well, but the reason why it happened is because if you find the partial derivatives of the right hand side and the partial derivative of the right hand side with respect to y is undefined at the given point, so which means that the right hand side is not continuously differentiable in a neighborhood of the initial point, and therefore this Picard-Lindelof theorem is simply not applicable to this initial value problem. Okay, so and here is a little quiz for you about